Hello, my name is Sivani Satya Sai Naga Vemparala, and for my Polygence research project, I calculated the maximum thrust that can be generated by a cosmic ray source incident on my model ionic thruster using OpenMC. I live in the country of Bahrain, and with the help of my mentor Soha Aslam, I was able to use OpenMC to run tallies on suitable parameters required for my model as well as achieve the desired results, that is, to find the amount of thrust that is generated by my ionic thruster. Without further ado, let's move into the background of this project. So, three things you need to know here: what an ionic thruster is, what are cosmic rays, and why am I using OpenMC? So an ionic thruster is a type of engine that ionizes propellant, commonly xenon because of its high atomic mass and easy ability to get ionized, by bombarding high energy electrons emitted from a metal filament heated to extreme high temperatures, known as thermionic emission, so that the xenon atom can be broken down into xenon protons when the electrons bombard it and can be accelerated towards the back and produce plasma as per required. This is the design of the gridded ion thruster or the Kaufman ion thruster, which I will be using opposed to the Hall effect thruster because of its ability to generate high thrust to power ratio as well as its longer period of operation. Cosmic rays are high energy particles originating from space, especially so events that are extremely energetic and violent, for example, supernova explosions or black holes, and they're traveling through space at nearly the speed of light. So the composition of cosmic rays has been given on the slide and is crucial so that my model can be tallied as per it. Now, I will be using OpenMC, as I've stated on the previous slide, why, to run suitable parameters on neutron flux or heating or absorption to produce data that can help me calculate the thrust that my engine model can generate. So what is the research problem? Cosmic rays can be efficiently converted and captured. Why am I making a model so that this process can be made feasible? It's because it cannot be done. Cosmic rays are extremely random in nature. They're very isotropic. That means the distribution throughout space is very uniform, and they cannot be focused into a parallel beam. When you incident light on a convex lens at the focus, you can expect to produce a parallel beam of light, just like how you need to produce a parallel beam of thrust for it to be operational. But you cannot do that with cosmic rays, which is why, as well as the technological constraints that limit the ability to even look at this direction, I have proposed an ionic engine model. Why not manipulate the cosmic rays to produce certain particles when they're incident on an array of materials and use those particles to ionize the xenon propellant instead? Let's see how. My proposed ionic engine model has three steps. The first one being spallation and alpha particle bombardment on the first layer, which is the beryllium foil. Now, spallation is a type of violent chain reaction or a cascade process wherein high energy protons bombard high atomic mass elements such as lead, tungsten, or even low atomic mass such as beryllium foil to produce a large number of neutrons with exceedingly high energies, more than the incident high energy proton over here. Now, spallation, however, produces beta positive decay in the case of this reaction, as well as a boron 9 radioactive isotope, which, yes, decays to produce a beryllium atom through beta positive decay, as I have just mentioned. Now, this radiation has to be stopped somehow because it'll penetrate and destroy the material, which is why I'm using water as the second layer. Water performs two duties over here. It acts as a moderator, helps in converting these fast neutrons into thermal neutrons by slowing them down, as well as shielding against this penetrating beta radiation and protecting the spacecraft. Now, the thermal neutrons that have been generated have to produce alpha particles, and that can be done by incidenting them on a boron layer or a boron foil, which through the process of thermal neutron capture produces alpha particles and a lithium atom as well. One advantage in the first layer is alpha particle bombardment on the beryllium foil using the 15% of alpha particles from a cosmic ray source produce a stable carbon-12 atom as well. What is the advantage of this? At high temperatures, carbon-12 atom, since it's heavier, will settle down and react with tungsten to produce tungsten carbide, a material with extremely high melting point and impact resistance, and it will most certainly improve the performance and structural integrity of this entire model, which is, again, a benefit without pushing up the costs. This is my constructive solid geometry, or CSG model. As you can see over here, it's a cylinder enclosing two spheres in the form of a hexagonal lattice. So you can see in the XZ and the YZ model that the incident neutrons are first moving through water and then they are passing through boron, which is exactly what I need. Now, some certain assumptions have been taken for this model, but the most important ones I would like to focus on here is, first of all, the model is 100% efficient, and spallation is producing double the number of neutrons, as I previously mentioned in the slide. And the neutron constituency as well has been defined here. That is, 80% of them have an energy of 20 mega electron volts, and 10% or 15% of them have an energy of 10 mega electron volts, which is extremely important to determining the results of my thrust, the thrust which is being generated. Another one here is the power consumption. 12 kilowatts has been set as per literature again. And the time interval between successive collisions has been taken as 0.01 seconds, which will be converted into 1 second while I'm doing the calculations. The tallies that I have taken for OpenMC: neutron flux, heating, absorption, and thermal neutron capture boron. Out of these two, I would like to highlight the graphs of neutron flux and heating as the primarily important graphs of this research paper. Now, if you can see the neutron flux graph clearly, the amount of neutrons passing through water is relatively lower compared to tungsten, where you can see a skyrocketing slope of the number of neutrons. And even for boron, which starts off with a higher number of neutrons, neutron flux as compared to both the other materials, reaches an ultimate maximum or a high, reduces gradually, and just like the other two materials, extends to infinity towards the end. That is, when the neutron energies exceed 10 mega electron volts. Now, the heating graph over here poses a problem, which I'll be discussing at the end of this presentation. So if you can notice, despite of whatever heating the materials are starting with, at the end of the day, at incident energies of more than 10 mega electron volts, they're skyrocketing to infinity. So before I discuss the problems with that, let's see the absorption graph. Now, there's no sign of boron on this graph. So one possible explanation for this is that the neutrons are completely being absorbed by water and converted into new thermal neutrons so that boron can efficiently utilize them and capture them for the reaction that it will be proceeding with. So that's a good sign. And the thermal neutron capture of boron is happening at extremely high reaction rate, which again is a good sign for my model. Now, the thrust can be calculated by a simple formula: exhaust velocity into propellant mass flow rate. Now, in my assumptions, I did discuss that the operating voltage I will be taking for my model is 1000 volts, although typical operating voltages are 1100 to 2000 volts. So using that, I calculated the exhaust velocity, and the propellant mass flow rate was calculated using the data that I obtained from OpenMC. And this product of these two quantities gave me a total of 0.66259 newtons. Now let's see what is the meaning of this data in my conclusion. The thrust obtained is actually higher than most thruster designs are able to achieve nowadays. Common thrusters have a typical operating range of 25 millinewton to 50 millinewton. But hey, one thing to note here is that this is not the actual thrust generated by the model. This is not reflective of the amount it can potentially produce, because I took low energy incident neutrons in for the cosmic rays, as well as the fact that this is just for 1 second. Now, thrust can be achieved, thrust can increase for 10 seconds, for 100 seconds, depending on the number of incident neutrons, and if the same rate of incidence is maintained, that is every 0.01 seconds, 17,500 particles are incident on the thruster. And one thing that I would like to discuss here, or rather a few things, is the limitations of this model, which does not discuss heavier and light nuclear collision with the thruster, because that produces a number of radioactive isotopes and would further complicate the calculations that I will encounter in producing this model, which is why they have been avoided for now. Also because their composition is minute. Now, the heat resistance, as I would mention, of both tungsten and water has skyrocketed to a very high amount when the incident energy has exceeded 10 mega electron volt. Now, this is a problem because it can compromise the structural integrity of the design, which is why their feasibility as a material will also reduce with increasing neutron energy. So future work for this model must include search for suitable testing facilities or centers that can simulate the model in those extreme physical parameters or conditions like high stress, high temperature, high pressure, and apart from that, can figure out and evaluate the scope and practicality of the design using these various parameters. And that's all for my Polygence project. Thank you.